Welcome back. Today we're diving deep into one of the biggest secrets in the universe, the incredible power packed inside the nucleus of a single atom. We're talking about a force that can light up our cities or power the stars themselves. So yeah, let's get right into it.
Just let that sink in for a second. Powering an entire city with something you could hold in your hand. And no, this isn't science fiction. That's the kind of mind-blowing scale we're talking about with nuclear energy. So, how do we even begin to tap into that? Well, it really boils down to two very different approaches.
And right here you see the fundamental split. You've got fission, which is all about breaking things, splitting them apart. And then you have its total opposite, fusion, which is all about joining things together. Two completely different actions, but both unleash an absolutely staggering amount of energy.
Okay, so let's kick things off with the one we've actually figured out, the one we're using right now. We're talking about nuclear fission. This is the science that powers every single nuclear reactor on the planet today. So what's the key here? Well, it's all about using a heavy atom. Think of big elements like uranium or plutonium. Their nuclei are, well, they're beefy. They're large, they're dense, and critically, they're just a little bit wobbly, a little unstable. That makes them the perfect thing to try and split apart. So how do you actually get this thing to split? It's almost ridiculously simple. All it takes is one tiny little particle, a single neutron. It's like the gentlest of pushes on a domino that's already teetering. That one little tap is all it takes to make the whole nucleus unstable and kick off this incredible reaction. And this is where the magic really happens. See, when that first neutron hits the uranium nucleus, it doesn't just split and release energy. It also spits out a few more neutrons. And what do you think those do? That's right, they fly off and hit other uranium nuclei, which then split, releasing more energy and even more neutrons. It's this incredible domino effect, a self-sustaining chain reaction that just builds and builds, releasing massive amounts of energy.
Okay, but here's the really important part. This chain reaction has two modes, controlled and, well, not controlled. If you manage it very, very carefully, like we do in a nuclear power plant, you can use all that heat to boil water, turn a turbine, and generate electricity nice and steady. But if you just let it go, you get an uncontrolled reaction. And that's an atomic bomb, a massive, instantaneous release of energy.
So, you might be wondering, where does all this energy actually come from? It all comes back to this famous equation, E equals mc squared. It tells us that mass and energy are basically two sides of the same coin. When that uranium atom splits, the pieces that are left over actually weigh just a tiny, tiny bit less than the original atom. That little bit of missing mass, that's the m, gets converted into a huge amount of energy, the E. All right, so that's fission. That's splitting atoms right here on Earth. But now, let's look up. Let's talk about the engine that powers the stars themselves, the cosmic powerhouse that fuels our entire solar system. Let's talk about nuclear fusion.
So remember how fission was all about splitting big things apart? Well, fusion is the exact opposite. Here, you take super light atoms. We're talking about special versions of hydrogen called deuterium and tritium, and you smash them together with incredible force. And the result? An even more powerful release of energy than fission, a lot more.
And this isn't some far-off theory. It's happening right now, every single second, in that giant ball of fire in our sky. Our sun is basically one gigantic fusion reactor. It's constantly taking hydrogen atoms and crushing them into helium. That process is the reason we have light, heat, pretty much life itself on Earth. So the obvious question is, why don't we just, build a mini-sun here on Earth? Well, for starters, there's the heat. To even get fusion started, you need to hit temperatures of about 15 million degrees Celsius. That's just insanely hot. Trying to create and contain that kind of heat is one of the greatest scientific challenges we've ever faced.
And honestly, the temperature is just the beginning. You also have to somehow overcome the natural repulsion between atoms. Think of it like trying to force the north poles of two super strong magnets together. They just don't want to do it. Then you have to hold all this fuel in a state called plasma, which is so hot it would instantly vaporize any container you try to put it in. And even if you solve all of that, you still have to figure out how to actually capture the energy that's released. It's a massive, massive challenge.
Okay, so we've got these two incredibly powerful processes, one we've mastered and one that's the holy grail of energy. Let's put them head to head. The ultimate showdown, fission versus fusion.
This right here breaks it all down. Let's start with the fuel. Fission needs rare stuff, like uranium. Fusion, it just needs versions of hydrogen, which we can literally get from water. It's the most common element in the universe. Then there's the energy output. Fission is powerful, no doubt. But fusion, it's on a whole other level. But here's the real kicker, the thing that makes everyone so excited, the waste. Fission creates nasty, long-lasting radioactive waste that we have to store very carefully. Fusion's main byproduct is helium. Yeah, the harmless gas you put in party balloons, and that right there is why fusion is the dream.
So, where does that leave us? What does all this mean for the future of energy?
It really comes down to this. Fission is our present. It's a technology that works right now, and it gives us a huge amount of carbon-free electricity. Fusion? Well, fusion is our potential future. It's that holy grail of energy, practically limitless, incredibly powerful, and clean. If, and it's a big if, we can ever crack the code.
And so that's the big question we're left with, isn't it? Fission is powering our world today, but could fusion be the thing that powers our tomorrow? The dream of bottling a star, of harnessing that incredible cosmic power right here on Earth. It's one of the greatest scientific quests we've ever undertaken. And if we succeed, it would literally change everything. Thanks so much for joining me.